In my previous video in the playlist, I mentioned something called the Maxwell construction, which allows us to use the plot of the van der Waals equation of state on a volume and pressure plot to find the vapor pressure of a given substance at a given temperature. But in order to use the Maxwell construction, we need to find the roots of the cubic equation of state and then use these roots to integrate the area under the curve defined by the van der Waals equation of state. So in order to find these roots, we need to turn the van der Waals equation of state into a usable form that we can plug into the Cardenas formula. And the Cardenas formula will then allow us to find the roots of our van der Waals equation of state and then use these roots to solve for the area, which consequently then we can use to solve for the vapor pressure or the temperature, the vapor pressure at a certain temperature. So let's start by transforming our van der Waals equation of state into the a usable formula for the Cardenas equation. So, as we know, the van der Waals equation of state looks like something like this. It's B minus A over B minus epsilon B times V minus omega. So we want to get this equation in terms of the compressibility factor. And we know that the compressibility factor right now is equal to C, which is equal to PV over RT. So if we multiply everything, both sides of this expression here, we can get PV over RT is equal to the opposite side. So we'll have Z equal to the other side. So we're going to multiply everything by V over RT. So Z equals PV over RT, which equals the RT will cancel out here, and we're left with V over V minus V. And then on this side we have A V times RT times V minus epsilon B times V minus omega B. And then next thing we can do is we can factor out a V from this expression here to simplify it a little bit. So we have 1 over B, or no, not B. We factor V out here, V minus V. So it'll be 1 minus B over B for this term here. And then on this side, we can pull a V out of both terms here. So we'll get left with A V over RT V squared, because we're pulling both these V's out. V squared times 1 minus epsilon B over V times V minus omega B times 1 minus omega B over V. And then we can notice the B's cancel out here, so we're left with Z equals 1 minus 1 over B minus A over R B V and 1 minus epsilon B over V is 1 minus omega B over V. Now we have a B that appears a lot in this expression here. So we know that due to the compressibility factor, C equals P V over T, Z R T over P is equal to V. So what we're going to do is we're going to substitute this value for V into the expression and simplify it for us. So we'll go back up here. So we'll have Z is equal to 1 minus 1 over the inverse of B. So it'd be P B over ZRT. And then that's going to be minus A over RT times ZRT over P times 1 minus epsilon BP over RT times 1 minus omega BP over RT. So that expression looks really complex, but we can simplify it a little bit here. In the second term here, z is equal to, still the same first term, 1 minus PB over ZRT, but minus, we're going to take this ZRT, this becomes Z R squared T squared over P, and we're just going to multiply, we're going to carry this out and take it to the numerator, so it'd be PA over Z R squared T squared, and that's still going to be over these two terms here. So we're going to have over 1 minus epsilon EP over RT times 1 minus omega EP over RT. Okay, now we realize we have a few terms that appear a lot in our expression. We have this B over RT term, or not B over RT. Wait, we actually know BP over RT. BP over RT. Sorry, it should be over RTZ, with the Z term. All right, yeah, BP over RT here. And then not the same, we still have RT in expression in there. So we want to simplify BP over RT by saying it equal to a different variable, and we'll say it's equal to beta. Beta equals PP over RT. And then this expression here is also a little complicated. So there's a common relationship between the two. We still have P in the denominator and RT term here, but we want to somehow simplify it out by saying, we'll call Y is equal to A over RT B. Okay, perfect. And then if we multiply Y times beta, these B values will cancel out, and we're left with PA times RT squared, and then we still have that Z constant there. So let's go ahead and plug these substitutions into our equation now. And we're left with Z equals 1 over 1 minus beta over Z minus, this will be Y beta over Z times 1 minus epsilon over epsilon beta over Z, and then minus 1 minus omega beta over Z. And then now, if we still have these Z terms in the denominators, so we're going to cancel these out by dividing each side by Z, or multiplying by 1 over Z, whatever you want to call it. So we're like left with 1 equals 1 over Z minus beta minus Y E beta over, and then since we have Z squared here now, we can distribute it to all these terms here. So it'll be Z minus epsilon beta times Z minus omega beta. And now we can go ahead and we can start working on solving this expression. We want to multiply a quadratic, or not quadratic, a cubic equation by both sides to cancel out both these roots here. So the expression is going to be for this quadratic. All right, I just finished recording and I realized it was hard to see and I ran out of space. So we're going to do this whole step again. So we get to the point in the equation where we have 1 is equal to 1 over z minus b minus y beta, actually this is beta, z minus beta minus y beta over z minus epsilon beta times z minus omega beta. And how we're going to solve this and turn it into a cubic equation is by multiplying each side of this expression by the cubic equation that we get by multiplying the denominators together. So by multiplying the denominators together, we're going to get z minus beta times this quadratic expression, which is z squared plus, it'll be epsilon minus omega beta, or no, epsilon minus omega beta squared, epsilon minus omega beta, this is beta z, and then this is minus, or no, plus epsilon omega beta squared. And it's all going to be equal to this term multiplied by this term, this big term. So these z minus b's will cancel out, so we'll end with, again, the quadratic. So it'll be z squared plus epsilon minus omega times beta times z plus epsilon omega b squared, and then minus this term multiplied by this term. So the quadratic will cancel out in this equation, and we're left with y beta times z minus beta. And then now we want to derive the different parts of the cubic equation of state, the different coefficients. So we're just going to go down here. We'll say this is column for z cubed terms, this is z squared terms, this is z terms, and this is our coefficient 1. So how we're going to do this is we're just going to go ahead and figure out what terms will give us the terms for each column by when we multiply through for each side of the expression and then shift the side to the other side. So it'll be these two terms will give us z cubed. These two terms will give us, no, they won't give us, oh yeah, they will. It'll be epsilon minus omega times beta. And then the third terms here will give us epsilon omega times beta squared. And then now we take this beta term here and multiply through. So we'll get a negative beta. We'll get a, for the c term here, we'll get epsilon minus omega times beta. And then here we'll get a constant e omega beta cubed. And that's it for the left side of the expression. And then let's move over here. We get a z squared term, which is 1. We get a z term here. So it's, oh sorry, it's a negative 1. Because we're going to move it to the left side of the equation, we have to subtract with the negative 1 here. Same for this one, it's going to be negative minus epsilon minus omega times beta. And then we have our constant here, which is going to be a minus because we're subtracting again, minus epsilon times omega beta squared. And then we want to multiply through for the expression to get a z term. So it'll be plus y times beta. And then we get a constant. It's going to become plus y beta squared. Then move to the left hand, it's going to be negative y beta squared. So these will be the coefficients. This should be c cubed, that should be a 1. Okay. These should be the coefficients for each of the terms in the equation that will be used to find the roots of the van der Waals equation of state. All right, so now that we have our cubic equation state that we derive from the van der Waals equation in terms of the compressibility factor, we can now finally take this over to Python and we can use the plot that we derived in the first part of the playlist, and we can use the Cardano's equation to find the roots of our cubic equation state, and then plug these roots in to use a Gaussian quadrature and the Maxwell instruction to find the estimated vapor pressure of our of water here. Let's plot it out at a certain temperature. So in order to do that, we need to first define the cubic equations, or the Cardanus equation to find our roots. So let's start by defining cubic underscore roots, and it's going to take in a value of a, b, and c, because those will be our coefficients in a cubic expression, cubic equation. And I'm going to pull this up because I will not remember the values of q, but here it's okay. So here's the Cardanus equation here, and okay, we have q is equal to a squared minus 3 times b all over 9. We also have r is equal to 2 times a power of 3 minus n minus 9 times a times b plus 27 times c. This is all divided by 54. And then we have kind of a conditional here. So we say if q and r are real, which we are going to assume they are going to be real roots, and if r squared is less than q to the third, comma, or colon there, so theta will be equal to np dot arc cos of r divided by it's going to be r divided by q, and q can be to the 3 hats power. So that will return our roots if oh wait, so that's what theta is, and then our roots if r squared is less than q to the third power. Here are our roots here. So our roots will be, we want it to return negative 2 times np dot square root of q times cosine, no, np dot cos, and then we want it to be multiplied by an array, because we're going to change these values here in the center, but everything else in the expression is going to stay the same. So np dot array, and in the array it's going to be theta divided by 3 theta minus 2 times np dot pi. I want to put this in parentheses because I don't trust order of operations here. Divided by 3, and I'm just going to copy and paste this for the third term, comma, plus 2 pi. And then each of those arrays are going to have minus a over 3 attached to the other them. So that takes care of the first case, but let's say r squared is not greater than q to the third, else say a equals negative r plus r squared minus q to the third, and that expression is raised to the power of 1/3, and this expression is all raised, oh no, this expression is raised to the 1/2, and this expression is raised to the 1/3. We also have another if statement. So let's say we have a value of for a value v or b here, to return this expression here, it will depend on the value of a. So b equals 0 if a is equal to 0, and if not, it's equal to q, which is defined above, divided by a. And then as we wanted to return x1 here, that'll be the one root, the real root here. It'll be a plus b minus a divided by 3. So there you go, we have our Cardenas equation here that will allow us to find the roots of our cube equation of state that we derived with the compressibility factor. But now we need to define a function that will allow us to find a, b, e, and s, which these are all dependent on the equation of state we're using. But the most common ones that we're going to be encountering are the van der Waals equations and the SRK. But for now, we're just going to code it in as a dictionary because we could be working with the other functions or the other equation of state down the line. So we're going to call this define calculate underscore a, b, and s. And it's going to take in t and the equation of state. But by default, we're going to use the SRK equation. So we have, in this expression, we have alpha, sigma, epsilon, omega, and psi. We don't really counter the compressibility factor much, so it's not going to affect us too much. And then we also have these two terms up here, a and b. So we'll keep an eye on those. And then let's code this out. So we'll start with sigma here. So s is equal to, and then here I will say v dw, and then comma SRK, and then at the end we're going to code in the EOS. We're going to be doing something a bunch of times, so I'm just going to, not that part. I'm going to copy and paste this, and we'll keep using that. But S in this sigma is 0 from the van der Waals, and 1 for the SRK. And then we'll say epsilon is equal to, both these values are 0 in this expression. So there's a 0 and there's a 0. And then we have omega is equal to, the van der Waals equation of state is 1/8. And then the other, it is 0.08664. Not done yet. Omega psi is equal to 27/64, and the SRK is equal to, or 0.42748. And then alpha here, alpha is equal to, same thing, van der Waals. We have 1, and this SRK expression, we have a function for the value of alpha. So it's here. So it's going to be 1 plus, parentheses, 1 plus 0.480 plus 1.574 times w minus, which is the eccentric factor of water, which can be derived, I believe, I don't remember exactly how it can be derived, so I'm not going to speak on it, but times w squared. And then we don't have the eccentric factor derived. These are our values that we have up here for some of the values for water, which we have the critical temperature and pressure, and obviously the ideal gas constant. So this will be called the eccentric factor. I might be spelling that wrong. It's an A. And then this expression is multiplied by it shouldn't have an end yet. Okay, good. Times T minus TR, which is the reduced temperature, to the power 1/2. And then need one more parentheses just to set this squared. And then TR needs to be defined. The reduced temperature is just the temperature divided by the critical temperature. That's why we had to have an input of temperature there. So I think this is right. Let me just double check. 1 plus 0.4 I believe that's correct. So, and we also need to find A and B here. So A up here, and we'll say B is equal to, what am I typing? B is equal to omega times R times TC divided by PC. And let's put this in parentheses because I don't know if that syntax will work. And then A is equal to this expression here, which is psi times A alpha times R squared times TC squared. So that will, and then we're going to turn A, B, E, and S. So that will return the different values of the A, B, E, and S constants in our expressions depending on whatever equation of state we want to use. And we're looking to use the SRK equation of state to solve for our, to estimate our vapor pressure here. So we're going to hard code this or set the SRK as a default here. So the next thing we need to do is define the actual cubic equation of state. So we'll just define cubic underscore pressure, and it's going to take in a value of volume, temperature, and the equation of state. So what's that? Okay. And A, B, A, A, B, E, and S in this expression will be equal to the what we calculate in this expression here, in this function. And then we'll go ahead and return R T, or R times T, divided by V minus B minus A divided by V plus E times B divided by V plus S times B. Is that from, that's not what we want. I don't know how they got an expression, but I guess we'll have to do with it. So now we're done with this. Get the full screen. So we have our cubic pressure and our A, B, and S, whichever cubic equation of state we want to use. We have this function to give us the values for A, B, and S in those expressions in these equations, and we have this function to find the roots of our the equation we derived. So now let's use the expression to find our roots. So let's define cubic volume, and it's going to take in pressure, temperature, and an equation of state. And like the other function, it's going to start off by A, B, and S equals calculate underscore A, B, and S. Calculate. I should have the inputs here. function. Calculate A, B, and S there. And then what do we want to, or our Z's are, if you remember from our last part of the video, we found the different Z's, and I wrote them down on the whiteboard, but I'm gonna pull them up. We put them in a spreadsheet, not a spreadsheet, here. So I didn't have to remember them off the top of my head. I put them here. So we derived these already. How can I split the screen? Here. And then Z's will equal, we don't want the actual values of Z. We want the roots of this function. So we want cubic underscore, or no, yeah, cubic underscore roots. And then for A, B, and C, we're going to input the function are these values. So we'll have E plus S times beta minus 1. Oh, we have to define beta and Q first. So beta is equal to B times P divided by R times T. And then we also derived these earlier. Q is equal to A divided by B times R times T. You would derived these earlier in the video. We're just putting these into code now. So there's, okay. So we had Z, the Z squared function down. So now we have to add the other part of it. E times S times beta squared minus E plus S times beta squared minus E beta squared minus E plus S times beta plus Q times beta. And then our last will be minus E times S times beta cubed minus E times S beta squared minus Q times beta squared. Let me just give this a quick read over because I don't want to make any mistakes here, and there's a lot of terms. So cubic roots. First, E plus S times beta minus 1, perfect. E times S times beta, or beta squared, minus E plus S times beta squared, minus E plus S times beta plus Q times beta, perfect. Minus E times S times beta cubed minus 3ES. Oh, should be minus, yeah, minus ESB. Okay, it looks right. So, and we want it to return the values of Z times P, no, times R times T divided by P. And that will give us the different volumes there. All right, so now we should have everything we need to go ahead and move forward to get our roots of this function and then plug them into our to use the Gaussian quadrature to solve for the different areas and then estimate the vapor pressure. But let's see how this function works before cubic underscore V, and let's see what it returns. Let's say 10e to the 6, and it's at like 6. 2 potential arguments B and C. Oh, I didn't mean to cut this out. Valid syntax, line 8. What's wrong with this? That or something? You don't have close parentheses there. All right. So it returns some different values. It gives us, we can check these values here. Let's move this plot up. All right, so let's see how these values check out. We'll kind of clear out 600 Kelvin to see if we can get a better view of it. Okay, so 600 Kelvin here. The roots are, so 4.2635 times 10 to the negative fifth. So there's one root around here, yeah, that looks right. 7.92 times 10 to the fifth. Right around, wait, here's one root up here. Here's the second root up here. And then third root, 3.9, somewhere over here. So yeah, it looks like our function is giving us the right values. So let's go ahead and define the function to find the areas, the Gaussian quadrature. So now we're going to say define Maxwell. We're using this Maxwell construction, so we'll call it Maxwell area. And we want to define, it's going to be pressure, it's going to be temperature. Does it need volume? I think it needs volume, not temperature. And as always, oh, so we want the different roots. We want the volume of liquid, we want the intermediate volume, and the volume of gas. And that's just going to be equal to cubic underscore V P T and EOS. And then in order to do this, we need to import a function from SciPy dot integrate. You would import what's it called? Quad Gaussian quadrature. All right, so quad, and then where's our box here? Here. So we wanted to return quad lambda v, and what was lambda v? It's like kind of a, we don't have to define a function, but it is a function in its own way. So the first thing we're looking for is the pressure minus the cubic equation state. So if you pressure that we input minus cubic underscore P. Oh wait, we want temperature, not volume here. Cubic underscore volume, that's on temperature. What do we have? Cubic underscore pressure, volume and temperature. Volume, temperature, EOS. And then we want to set the limits of integration here to VL and VM. And we also want to return lambda, or no, quad, another quad, lambda v, same thing, new function, but this time we're doing the cubic pressure because it will be above the pressure line we choose, the certain pressure, cubic underscore p, and volume, temperature, state, and then comma, so we wanted the v middle, the intermediate volume to the gaseous volume. So there we go. We have our function Maxwell areas. So let's try it out. How do I move this thing up? I don't want that so far down there. Boop. All right. So return. So Maxwell underscore areas. So we're at 600 Kelvin. What pressure will kind of split this line up here? What do you think would give us a decent value? Somewhere in like 100. That's 100 times 10 to the what? Third? Yeah. 10 to the sixth. 600 Kelvin. I think I might have put. Yeah, that's right. 98. What's wrong with this? Float object is not callable. Go all the way back up here to cubic roots. What's wrong with our function? Negative 2 times n plus 1. Close the array. Close that. Let's try a smaller temperature, see if it changes anything. Oh, we wanted to say, okay. We only want the first value because we're just going to return a guess and something else. So we want 0 and 0. It's a little off, our guess. So let's keep adjusting the temperature, the rate pressure until we get a better guess. Something's off. So that's not exactly equal. So something's wrong with our code here. Let's try to figure out what we did wrong. Oh, we don't have minus pressure on this side, do we? All right, that's pretty equal. Let's keep adjusting it further from the. That's pretty good. Say 90. Say 9,500. 9,600. 9,650. 9,655. Butt in there. 9,660. 90, 60, 57. All right, well, it's not budgeting very much, but from this function here, we get an estimate that the vapor pressure of water at 373 Kelvin is closest to a value of around 90,657 pascals. So that's our estimate there. And we know this because this function here defines the Cardan's equation, which we then used to find the roots of our equation of, or a cube equation of state, and we found 3 different volumes, which we then plugged in here, and these volumes became our limits of integration of this curve, or not this curve, but here we can just highlight 375 because that's the curve we're looking at. .375 here, this curve. So that's the curve we're looking at around 375. So that curve here. So we found the limits of integration, and then using the Maxwell construction, we plotted an imaginary line of around whatever 90,000 pascals, and then that gave us the line that we used the Gaussian quadrature to integrate and find the areas under the curve, and we found that around 90,657 pascals, that these volumes were, these areas under the curves were almost equal to each other, and that means that an estimate for the vapor pressure of water at 373 Kelvin is around this number here.